Hi everyone, this is a quickish review of state space modeling. Let's see, the motivation for this. Primarily the motivation for us is for being able to simulate dynamic systems easily using things like Simulink. In other classes, multivariable control, it forms the heart of control system design. We'll be doing a little bit with that later, but mainly, we're looking at it from a dynamic system simulation perspective. Oh, I think I just said all this. Okay, so here's how it goes. Given some dynamic system like this, so here we have two second-order differential equations where the dependent variables are theta1, theta2. The input is tau, and it has a bunch of initial conditions. If you wanted to solve this thing, you could do it the hard way, or you could put it into, that is, try to get a closed form solution, or you could put it into something like Simulink and get a numerical solution. One of the interesting things about state space representations, or sometimes I'll say state space realizations, kind of interchangeably, are that they are not unique. And this causes some people a lot of heartburn. So this is one state space representation of that dynamic system, but it's by no means unique. It gives us an A matrix, and we know that the eigenvalues of that A matrix gives us, from looking at the linear algebra review, gives us the poles of the characteristic equation. So it's interesting that while the A matrix isn't necessarily unique, they must all have the same eigenvalues, because certainly the characteristic poles of the dynamic system wouldn't change just because we use a different state space representation. So that's an important note that we'll chew on as time goes on. Oh, little typo there, theta1. Okay, so the state variables, we'll call those x. I'll use the underline for a vector. We can think of it as a minimum set of variables. You can actually have more than the minimum set, but clearly a minimum set would be better than a non-minimum set. But it's a set of variables such that if you know the initial state, or the initial state vector, x0, and you know the input u, and of course you know the dynamic equations, then you can compute the time histories of those states for all time. So this is a very abstract definition of states, and fortunately, we're going to make this extremely concrete. So again, there's no unique state space representation. It leads us to a set of first-order differential equations of this form. We're going to convert those second and third and fourth order, whatever order differential equations we have, into a set of first order differential equations. That's the x dot equals ax plus bu, and the output equation, which is the y equals cx plus du. Once we have those matrices, assuming the system is time invariant, once we have those matrices, A, B, C, and D, we just plop them into Simulink, and boom, we've got ourselves a nice simulation. Yeah, a lot of times I'll use double under bars for the matrices. So here's the steps for doing a state space representation. First, you have to determine how many states you need. And the way to do that is you look at each of your differential equations in your system and sort of tabulate all the dependent variables. In that previous example, that was theta1 and theta2. And then you scan over those dependent variables and notice the highest derivative that they appear in. So let's say we had a theta1 triple dot and then a theta2 4 dots. Okay, so we have a total of 7 dots, and so you would need 7 states to represent that dynamic system. Then you have to define the states, and we'll see just some basics of how to do that here, and then in some other notes we'll get into a little bit more detail. That once you define the states, x1 equals such and such, x2 equals that, and x3 equals this, now you just take the derivative of x and represent that x dot in terms of the states x. And then you can also form the output equation. Actually, forming the output equation is easy compared to forming the state equation, so you may even want to just do that first. Here's just a summary of the size of things. So if you have n states, this A matrix is going to be n by n square. So that means we can invert it. Well, I should say that. That means that we can do all the things we can do to square matrices. It isn't so much that we want to invert it, but we can certainly do things like find its determinant and its eigenvalues and things like that. There's m inputs over here. Then B is n by m, not a square matrix. C is not in general a square matrix, and neither is D. A is the only matrix that is guaranteed to be square each and every time. Now for what we do, most of the time, the size of the input is going to be 1, and the size of the output is going to be 1. So M and P are equal to 1. So a lot of vectors instead of matrices. So let's beat on this example that we saw an answer to a few moments ago. If we look at our dependent variables, theta 1 and theta 2, it has a couple derivatives of each. So n is going to be equal to 4, and this is one legitimate definition of the states. There's an infinite number of ways of doing this. You can do it incorrectly, and we'll cover that in another video. So now you just take the derivatives of those states. Now first, I'm just going to rewrite the equations that we had on the previous page, where I've divided through by J1 and J2. So that's exactly what we had on the other page. So now we'll start in at it. So x1 is theta 1, take the derivative of that, so it's theta 1 dot, and then I represent that in terms of the original states. And if you recall from the previous page, that was x2. x2 is theta 1 dot, and so x2 dot is theta 1 dot. And now we have to go up and use the equation on the upper left in order to express theta 1 double dot, or x2 dot, in terms of x1 and x2 and x3 and x4. x3 is theta 2, x3 dot is theta 2 dot, which is just x4. And x4 dot is theta 2 double dot, and so we have to use our dynamic system equation here in order to represent that in terms of x. And, in this case, an input, tau. Now we have to form our state space equations, A, B, and eventually C and D. So let's go after the state equation first. What I'm doing here is looking at this equation. Right, that's the top row of x dot equals ax, and just noting that the only thing it's a function of is x2, and so that goes right there into the 2 slot. Now I move on to the next equation, which is this one, and fill in the x1, x2, x3, which is 0, and x4 slots. Now I'm on this equation. Pretty boring, just an x4. And finally, we're on this equation. And we have an x2 and an x4 piece. Find B, that's for this. I just look at where I have inputs in this system of equations, and the only place I have it is right there. So I'm just going to get that last element. And now we do the y equation. Probably should have done this first, but hey, that's the way the notes are laid out. So it was in the prompt, it said that the output is theta 2. And so that's just equal to x2. And I can form my output equation. And in this case, what I've done is I've just hogged out the space, if you will, to fill in C and D. I think that's probably a better way to do this. And so the x2 ends up in the 2 slot, and we're done. Now here's one that often throws people for a loop. First order differential equation, negative 3x plus 2u. The tricky thing is that this thing is already in state space form. All you have to do is just pull out the a, b, c, and d. They're just equal to a bunch of scalars. There's the a and the b, and if my output is x, that's just 1. Let's see, another example, very similar to the previous one, except we have a couple inputs, or the input is in a couple equations, I should say. The number of states is 5. We have 3 derivatives on the theta 1 and 2 derivatives on the theta 2, dependent variables. How about if I make these our definitions and start taking some derivatives? So that's theta 1 dot. x2 dot is theta 1 double dot, or x3. And for x3 dot, I have to go up to the differential equation here. And I just pull out the right digits. x4 dot is theta 2 dot, which is x5. And x5 dot, I have to use this equation. So I just throw all these to the other side of the equality, and away we go. Now we put it into state space form. Here I'll hog out the space first. Guess I should have a little underbar there. So looking at the first equation, we just get an x2. Looking at the second equation, we just get an x3. The third equation, we get some stuff, negative 3, a negative 7, a 4, and we pick up an input. How special is that? And for the x4 equation, we get this, and for the x5 equation, we pick up all those nice terms, and another input. The output, the prompt says theta 2 dot, that's just x5. Grab some space. Ran out of space actually right here. And in it goes. That's it. Oops. Hit the gas pedal too quickly. So this is our A matrix here. Here's our B matrix, our C matrix, and the D matrix. Now, here's a slightly interesting case. The only real difference from everything else we've looked at is that now we have the input not only a function of u, but also a u dot. Now, u and u dot are not independent. If you tell me u, I can tell you a u dot. If you tell me u dot, I can tell you a u, etc. Well, let's pick some states. The correct way to do this, or one correct way to do this, is like so. I'm setting x2 equal to theta 1 dot minus 3u. The reason for that is I'm thinking ahead. That is, I'm thinking to what's going to happen when I form x2 dot, and I have a theta 1 double dot minus theta u dot, and then all this stuff I can write in terms of x1, x2, and u. If you just let x2 equal theta 1 dot, you can give it a try on a scrap piece of paper or something, and you'll see that you run into a problem really quick. So give it a shot. So there's x1 dot, that's easy enough. It's just theta 1 dot, and I get theta 1 dot from here to write it in terms of x2 and 3u, or x2 and u. Next 2 dot is this. Now I can solve this equation for theta 1 double dot minus 3u dot, and again I get all the stuff here in the square box. Now I have to replace the theta 1 dot with the x2 plus 3u again from this, so that I get this right hand side all in terms of x's and u's. Uh-oh, what did I do? Okay. I'm just going to keep rolling. And so now I'm just doing some math, simplifying things down, gathering up my terms, whatever you want to call it, and go to put it into state space form. So I grab some space, no pun intended, and for the x1 dot equation, I get this wonderful thing, and the x2 dot equation I take from there. And my output is a theta 1 dot, so I get that from here. And I am done. So I have my A, B, and my C, and my D. All done. Very nice. I think that's it. Oh my gosh. Okay. It went so quickly. So we did so many things here, but basically a lot of examples in state space and how to deal with these little tricky cases where you have an input and time derivatives of inputs. Hope you enjoyed it. Hope it's helpful. Bye-bye.